He worked with ACC Limited for 32 years at various locations and in various positions. So the last position he held in ACC was GM Production. Thereafter, he worked with Imami Cement Nuvoco for 4 years as a senior vice president and worked with KJS Cement as a manufacturing head. So he has overall 37 years of working experience in cement manufacturing in different processes. And thereafter, he has been working as a end-to-end cement project execution person. So I don't think he wants us to call him a consultant, because consultant is more, theoretical, across the table discussion. He actually puts up the plant. So, and one more thing, before I forget, I remember the first time I saw electronic components like resistors and capacitors was in his house. He used to be a big time electronic buff as a school boy. I do not know whether he kept that hobby, and he would make various things in those days. And he wanted to take that up as a career, and I think his father must have dissuaded him later. So over to you, Dilip.
I would like to brief you first the history of cement, then the current scenario and future trends in cement industry, then evolution of cement manufacturing process and typical modern integrated plant, and then types of cement and key performance indicators. Because why key performance indicators put together to achieve all these parameters, lot of automation, instrumentation is involved in that. So here basically, if you look back, the cement first time was manufactured in England, and it was known as Portland cement. Basically, the color of the cement was like the stone in Portland, and the main person behind cement was discovery or invention was Joseph Esfidin. He was basically a British mason or a bricklayer, so he was the originator of cement. Then subsequently, in late 1824, 1826, they further tried to improvise the manufacturing process. So these were all basically static kilns. So in 1843, his son, Joseph Esfidin's son, also did some work on that and got it patented. That was first time. Then later, cement which was manufactured from that process was first used in some drains and sewages like that. Now, current scenario is that 4.4 billion tons of cement is produced and distributed annually, globally, throughout. Now, just a minute. So the main producers of cement are basically China, which contributes to about 2.5 billion tons, and US about 330 million tons, and India is 330 million tons and US is about 75 million tons. So Indian scenario, actually there are about 350 to 65 mini cement plants and about 139 large cement plants, and there are more than 42 operating players in this field, and the total installed capacity is about 330 million tons. So the growth in the industry is almost 7 to 12% annually. But now, because the forecast is on the higher side, because a lot of infrastructure jobs are being taken up by the government itself. So in India, basically, the major players are Adani now, which has taken over ACC and Ambuja. Then you have Ultratech, then Heidelberg Cement, Sri Cement, Dalmia, Nuvoco, and so on. The best part is that every year, almost 10 to 15% capacity is being added. So this is the global scenario of cement. You can just have a look at this graph.
So what used to be Lafarge, because we sold our cement plant, Tata Steel had a cement plant and they sold it to Lafarge. So what happened to Lafarge? It was taken over by Holcim.
They were taken over by Nuvoco. Nuvoco is that Nirma group.
Okay.
So even today, it's Nirma, the Nuvoco Limited is managing those plants, is running those plants. And Lafarge had merged with Holcim in 2014. After that, they have left India now, both Lafarge and Holcim, after selling their business. So cement industry basically the evolution, just a brief this thing. Initially, the cement was manufactured in wet process plants. So they were very primitive in nature with very low capacity of production. The plants were producing somewhere around, each kiln used to be about 350 to 150 to 350 tons. Then after that came the semi-wet process, which was basically a development of Lafarge in France. So there the capacity was slightly improved. It went up to 400, 500 tons per day. And again here the issue was in both these processes, water was being used to control the feeding of raw material. And that's why thermal losses were high. Then after that came the dry process kilns. So these dry process kilns had very low moisture, but again here the bottleneck was the production volumes. Later on came the most modern, that is which is now in operation everywhere. That is the preheater kilns. So you can just see the photograph of long dry process kiln. This kiln
Sir,
basically
sir,
the length
I'd
of,
like to.
yeah.
There is a vertical shaft kiln technology, no, sir. In between,
Mm.
we were talking about many plants with VSK technology. It falls under
VSK.
which category?
VSK basically is a vertical shaft kiln. It's a static process.
Sir.
Nodules are made and then they are fed into the kiln along with coke.
Okay.
So the production volume is very low. It is something like 100 tons per day. It comes under
Okay.
the small scale sector.
Is it happening nowadays? Are there VSK technology machines are available?
Some of the plants are operating, but they are not
Okay.
viable actually. They are very
Okay.
labor intensive because everything is done manually. Even
Okay.
feeding of limestone is done through labor. I have seen such units, but they are not viable actually. So this basically long dry process kiln. This kiln used to be about 100-120 meter long and supported by about seven supporting rollers. And here again the bottleneck was same. Though it was slightly efficient, it was better in thermal efficiency. But here again the volumes were low. So here you can see after the kiln there are cyclones. There are four cyclones. This is basically four-stage suspension preheater kiln. So this technology was proven and became popular after 70s. And after that, whichever plant was installed across the world, they have gone for 4 or 5 stage preheater plants. So here the thing is that the raw meal which is fed from top of the cyclone, it gets heated and then later it enters the kiln. So there is a huge saving in the thermal energy, which in the earlier process was not there. So this technology became popular. This is a 5 stage preheater circuit. Here you can see there is one additional device which is a calciner. So calciner basically was introduced in 80s, and after introduction of this calciner, these kilns which were producing about 1,500 ton per day started producing almost 3,000 tons per day. And today there
So,
are,
so just going back, what is fed from the top?
from the top the raw material is fed in the form of powder. The raw mix is fed into the kiln, which comprises of limestone and about 1 to 2% of iron ore and bauxite. So that raw meal basically gets calcined slowly. That's first it gets dried, then it gets calcined, and then it enters the kiln. So the clinkerization process takes sintering, which we call, happens in the kiln. You can see that flame here in the kiln. The temperature here is almost 1400 plus or minus 50 degrees centigrade. So after clinkerization, the hot clinker, it falls into the cooler, which is after the kiln, where you can see there are 4 fans at the bottom. Just for indication, there are normally 7 to 9 fans in that cooler system. So here what happens is the cold air, the atmospheric air, cools the clinker and the heat is exchanged and taken back into the pyroprocessing system. So there is a huge thermal saving. So in this process, basically, the thermal energy consumption is about 680 to 700 kilocal per kg clinker as compared to 1000 kilocals in the dry process kiln. And in wet process, it used to be 1600 kilocal per kg clinker. So this is what this technology has given advantage over there. So basically, this is the entire flow sheet of the typical modern integrated unit. On the top, you can see there is a quarry, that is the limestone mines, where the limestone is raised from the mines, and then you have a crusher. After that, after crushing, the limestone is stacked into pre-blended piles over there. That is, we call reclaimers. So from reclaimer, after pre-blending of the limestone, basically the pre-blending is done to achieve a targeted LSF. We call it as LSF. That is the lime saturation factor. So that is the basically control parameter for the raw meal and also for clinker. So here, after that, this limestone which is extracted from this pile goes into a raw mill. So raw mill, basically, you can see on the right hand side, there is a raw mill. The raw mill grinds this limestone to a fine powder, almost of the size of say 20% on 170 mesh. From here, basically the raw mill powder goes into the silo, homogenizing and storage silo. Nowadays it is known as CF silo, continuous flow silo. So here, after homogenization is done by blowing air from the bottom into the silo. So the entire raw meal gets mixed, and from here the raw meal is lifted and fed into the top cyclone of the preheater. So from the cyclone, because of the cyclonic action, there is a separation, and the material by gravity comes into the next cyclone. The hot gases, they go to the next cyclone, and from there they make their way out into the from the system. So after that, the material enters the kiln inlet, and after clinkerization in the kiln, the material comes to the cooler, and from the cooler, the clinker which is discharged, this is basically the raw material for cement manufacture. If you add slag with clinker, it becomes slag cement. If you add fly ash with clinker, it becomes PPC, that is Portland Pozzolana cement.
So
And
how much slag can be added? The maximum percentage?
Bureau of Indian Standards has given a limit of 75% slag in slag cement.
Lime becomes lesser quantity.
No, this if you look at the slag which is used is also like clinker only, because it comes out of the blast furnace where you have same calcium aluminum silicates in that which we have in the clinker also.
Okay.
So slag has got hydraulic properties. So
So where is the slag added?
Slag is added in final cement grinding stage.
Not in the cyclone, not here, not in the kiln, later.
This kiln part is only for manufacturing clinker. So clinker is the raw material for cement manufacture. So you can make any type of cement after you produce the clinker. So from here, this clinker is stored in silos or other kind of warehousing system. And from there, it is again extracted and taken to cement mill. Cement mill is also just like a raw mill, where you decide what kind of cement you want to manufacture. So you use basically three raw materials. One is fly ash, one is clinker, and one is gypsum. Similarly, for slag cement, you have slag, clinker, and gypsum.
So what is the shelf life of this clinker? Because you are storing in big what you call
big silos,
storage silos.
Storage, almost 1 lakh tons storage is there for clinker storage.
And it flows on its own, gravity flow?
There are extraction gates at the bottom of the silo. There are about 13 to 14 extraction gates. And from there, and they are all controlled from the central control room.
So it flows in pipes, or it flows on what you call conveyor belts?
It flows into, actually we have two types of conveying system. One is conveyor belts, and other we have what chain feeding system. Because of higher wear rate and temperature, PVCs are preferred. They are made from actually spring steel. So that kind of a
Okay.
conveying system is used.
Cement mill, we are talking about Kambadan mill, ball and roller mill. I say bari technology baat kar rahe hain. Can you throw some light on that?
See, if you go back the olden days, so that time these VRMs were not developed. So we had only ball mills or tube mills where you have balls in that, different sizes of balls, 45 mm, 60 mm, even 100 mm. So these balls are basically, when the mill rotates, the balls they fall on the clinker which you feed from the inlet, and the clinker gets crushed. And then, and then you have another chamber in that mill where this clinker goes, and then you have fine balls for grinding it finer. So that's how basically that technology was there. But the only problem is again the throughput from ball mills is quite low. So far in India, what we have seen, ball mills are giving maximum 150 TPH from the cement. And now VRMs are there. So VRMs are capable of producing 500 tons per hour. And there is another technology which has edge over vertical roller mill is roll press. There are rollers which are hydraulically controlling the pressure, and the clinker which falls in between is crushed to fine powder, and then it goes to a separator where the desired fines are separated, and then the coarse material again comes back into the roller. So all these technologies have changed over a period of time, and these are the latest now, and they are more reliable, more effective cost-wise also, and productivity is better than the ball mills. So here we have got temperature indicators, that is thermocouple or RTDs at every point of the cyclone, the calciner, the kiln inlet. Then we have got pressure measurement points in all these areas. So the entire system is controlled from the CCR, and we have interlocks. If the pressure drop becomes zero at any of the cyclones, immediately the feed to the system will be stopped, and firing also will be reduced to more than 50%. So this is the kind of systems. Already automation part is there, but despite all this, there are chances when jams happen, and it takes almost 3 to 4 days to clear the jam and restart the plant. So this is one good opportunity if you can look into that.
Sir, one more thing I want to add here. There were a nucleonic gauge also that shows the filling percentage of that cone. How much material percent of the cone, total area of cone. So that gives the accurate reading of the material restriction inside the cyclone. Nowadays we are using in our cyclones. So that is the new systems we have installed in the scale system.
And one area which maybe very interesting for automation part, this kiln is almost 77 to 80 meter long. So once in a year or maybe twice in a year, we are required to do the refractory lining work inside the kiln. So the kiln lining basically is a very labor intensive job, and the unskilled labor keeps on laying the bricks, and somehow a system of placing the right brick and then ensuring the proper alignment of the lining. If something can be done, because this almost we are kitna labor lagta hai, Amit?
Around incomplete lining, sir, at least at a time 60 to 70 laborers are engaged
for 6
right
to
from
7 days. And these bricks are quite costly. They are imported bricks.
Yeah, lining is a problem in all steel plants, cement plants, everywhere, and the problem is the person who goes inside actually is not a very skilled person.
Cement plant lining is different from your blast furnace. Na? Inside the kiln, it's a complete tunnel-like thing. And if something can be done, because a lot of things have been done. Now there are tools for debricking the lining. Earlier, it was being done manually. Now it takes hardly 24 hours to debrick the entire 70 meters of the kiln lining. And there is a brick laying machine also. The bricks are transported on a belt cover up to the point. Then there is a jig over there, which where again labor is required, and it is placed on the shell, and then it is held hydraulically, and then keep on placing the bricks like that. So improvements are there, but this is one area which can be.
Sir, can you throw some light on the smoke chamber poking? This is what I mean. This problem statement what was discussed.
Nowadays, actually, we have installed air blasters at the kiln inlet and places where choking takes place. But when there is excessive imbalance in the system, even then there is a lot of coating at those inlet chamber as well as the riser duct above that. So again, the only solution is manually. Every half an hour, every hour, a person goes there, and it's very unsafe, very risky, because by chance, if the system gets pressurized, the fellow will be finished. So this is one area, yes, where it can be quite helpful. It requires frequent cleaning. Kiln inlet area, that chamber what you are talking about, na?
Yeah.
That inlet area often gets choked. There will be always some coating, and the moment the coating is cleared, there is an improvement in the performance of the kiln system also. When there is excessive coating, the feed of the kiln gets reduced. You can't run the kiln at higher feed. So it's a very promising area, and it is very unsafe. We were not getting sleep in the night just because of these safety issues. And Lafarge Holcim was very serious about safety. एक एक्सीडेंट हो गया तो साला नौकरी गई.
सर ये स्मोक चैम्बर पोकिंग वाला ये बाहर कैसे होता है, मतलब इन दी एडवांस्ड प्लांट्स और ऑटोमेटेड वे में कैसे होता है ये?
यूरोप वगैरह में क्या है, दे डोंट माइंड फॉर एनी टाइम थिंग, दे स्टॉप द प्लांट एंड क्लीन इट. इंडिया में क्या होता है, हमारे जो बॉसेस होते हैं, दे स्ट्रेस ऑन, अरे यार चलाओ इसको कैसे भी करके, रनिंग में करो, डू इट व्हाइल रनिंग. So that involves a lot of risk.
But ये हर घंटे 2 घंटे में उसको साफ करना तो ऐसे continuous process जैसा ही हो गया ना?
ये continuous है. I think most of the plants, this one person is dedicated for this job.
And this is the way world over?
See, there is a difference. The difference is that in Europe and Saudi and other places, they don't use coal. They use natural gas. Gas composition is by and large, perfect. The problem starts in India because our coal quality keeps varying. We get coal from different collieries. Then we crush and make a pile and blend everything. And then when we fire it, we come to know that there is some mismatch. Sometimes there is high sulfur in coal. And especially this plant where Amit is working, Dalmia, sulfur is how much? 4%. So sulfur is a very big contributor to this inlet jamming. But because it is a part of, if you go to this Sanghi cement, Sanghi has got, sulfur in the limestone itself. So what they can do, they have no other way out. So this you have talked about a very reasonable thing, because it's a big safety issue also. We have seen a lot of accidents in that. Many people have lost their lives also in this. The moment there is a pressurization and backfire, the fellow who is at the inlet, he's finished. Because air blasters help up to some extent, but beyond that also, sometimes it is so miserable coating, it becomes difficult to clean. And people take risk by, putting manpower and then all that. Though we use all safety PPEs for that, but still it's not safe. Because if there is a pressurization, in that ACC Camor plant, recently one fellow lost his job just because it was not in his hands. Something went wrong and the system got pressurized. And the person who was doing this poking job got burnt, almost 40% burn injury. This operator was terminated. So this is one gray area, and it needs some kind of automation.